Welcome to Make, a course taught at the University of South Florida. Electronics 101, Resistors, Voltage Dividers, and Power. This tutorial discusses Ohm's law, voltage dividers, power and power dissipation, and Kirchhoff's current law. Let's talk first about current, voltage, and ground. So here I drew a basic circuit. We have a power supply and we have a load. And when you think about a power supply, essentially on one end, on the negative end, we have electrons, and on the positive end, we have a lack of electrons that we can think of as positive charges. And so if we connect this load here, what happens is these electrons that have a certain potential energy that is proportional to the voltage, these electrons, they flow through the load and they go to the other side here where they fill those positive charges. So during this process, the potential energy of the electrons is dissipated through the load into the environment. So energy is coming from the power source, it's going to the load, and then the load typically heats up, and that heat is then dissipated into the environment. The higher the voltage, the more electrons, the faster the electrons are being pushed through the load, and that of course then generates a higher current. And so if we have a higher current, then we also dissipate more energy, so the load would get hotter. The ground, that is just a convention. So any circuit, one defines one point of the circuit as ground, and one defines the voltage at that position 0, and then all the other voltages are given relative to that ground location. So in this simple circuit, we would have here 0 volts, and since we assume here a 5 volts power supply, it would mean that up here we would have plus 5 volts. Had we put the ground up here, then of course up here it would be 0, and down here we would have minus 5 volts, because that is the negative end of this power supply. Note that for historical reasons, it is usually assumed that the current goes actually in a direction that is opposite to the direction that the electrons are really going in a circuit. So we always assume that the current goes from the positive potential to the negative potential. I just said that a higher voltage causes a higher current in a circuit, and that is essentially what is defined by Ohm's law. Ohm figured out that current and voltage depend linearly on each other. So the typical way Ohm's law is written, that the current is equal to the voltage divided by the resistance. So in essence, in this funny cartoon here, the voltage, remember, that is the energy that is proportional to the energy that tries to kick the electrons through the circuit, but the resistance curtails the current. So if we have two resistors, one with 1 ohm and one with 10 ohm, this is a current versus voltage graph. So in the 1 ohm case, the smaller resistor, here at 1 volt, we would get 1 amp of current. If we have the larger resistor in the circuit, then we would get a much smaller current. So in this case, because the resistor is a factor 10 larger, we would get 1/10 of the current. So only 0.1 amps instead of 1 in the case of the 1 ohm resistor. So if you think of a typical Arduino situation where we have 5 volts at a digital pin and something of the order of 1 kilo ohm as load attached to this pin, then we could calculate that we have 5 volts divided by 1000, and so that would just give us 0.005 amps, which we could also write as 5 milliamps. So if we put two resistors in series in a circuit, then we created a voltage divider. Voltage divider is probably one of the most important concepts in electronics. In essence, what it does is it scales the input voltage relative to ground into an output voltage that is smaller depending on the ratio between these two resistors. So if you wanted 2.5 volts but you only had a power supply that can provide 5 volts, you could put these two 1 kilo ohm resistors in series, and then in between them you would get a voltage of 2.5 volts. The formula for this is that the ratio between output and input voltages is just the output resistor divided by the total resistance. So just the ratio between this resistor and both resistors is the ratio between the output voltage and the input voltage. So the reason for this is that the voltage needs to drop from the 5 volts to 0 across these resistors. And so if we go back to this single resistor here, then it's obvious that somewhere throughout this resistor the voltage needs to go from 5 to 0. So if we would break this resistor here in half, then half of the voltage would drop up here and half of the voltage would drop down here. And so by using two resistors that have the same value, we create a situation where half of the voltage is dropping here and the other half is dropping down here. And so that means in this voltage divider where both resistors have the same value, we get exactly half of the voltage at the output. If we change these resistors to different values, then of course we can scale the output voltage from 5 to 0. Here I'm simulating the voltage divider in iCircuit, and let's see now what we have here at the output. So in the inspector window we can see we have 2.5 volts. Let's also look at the current that goes through the circuit. So we have 2.5 milliamps. That makes sense, right? If you divide 5 volts divided by 2000, these two resistors in series, they just add up, so we have 2000. That gives us just 2.5 milliamps. So let's put a different resistor value in here, and let's make this 2, and down here we also make it 2. And so what we see now is that the output voltage is still 2.5 volts, right? Because we have still an identical voltage drop up here and down here. So really what determines the output voltage is the ratio between these two resistors, not their actual absolute values. Nonetheless, something changed. If we click on the resistor and measure now the current that goes through the resistor, we have now only 1.25 milliamps, so half the current compared to the situation before. And that makes sense according to Ohm's law, because now we have 2 times the resistance in the circuit compared to having 2 resistors at 1 kilo ohm. So let's make this resistor a little bit bigger. Let's put 5 kilo ohm in here and see what the output voltage is. And so now you see the output voltage dropped significantly. We have now only 1.429 volts, and that is caused by having a larger resistor up here, which corresponds to a larger voltage drop, right, in Ohm's law. And down here we have a smaller voltage drop. So the voltage now is pulled down towards ground. If we reverse this, we can put here 2K and down here the 5 kilo ohm resistor, and we go to the output. Now we have 3.571 volts, so that's closer to 5. So you see, by changing the ratio between these two resistors, we can control the voltage at the output. Okay, so I went back to the original voltage divider where we had 1 kilo ohm down here and 1 kilo ohm up here, and so that gave us the 2.5 volts at the output. So I want to do a little experiment now and put down here just half a kilo ohm, and so what we see now is that the voltage dropped to 1.66. So let's keep this in mind, and we're going back here to 1 kilo ohm. So we're back to 2.5, and now I'm gonna connect this additional resistor in with the wire tool, and let's see now what we have at the output. And so it's the same voltage like what we had with the 0.5 kilo ohm resistor. So what happened is, with this second 1 kilo ohm resistor that I added in parallel, we basically lowered the resistance in the bottom part of this voltage divider, and those two 1 kilo ohm resistors in parallel, they end up with exactly the same effect like one 0.5 kilo ohm resistor. So it seems if we put two resistors in parallel, then that lowers the resistance in the lower part of this voltage divider. And that makes sense because you see here now that the current is actually branching into two paths. So we added an additional path for the current down here, and so of course this lowers the resistance in the lower part. What we also see is that all the current that goes in here and the current that goes into these two branches, that needs to be the same, right? Because down here they come back together, and what goes into ground is of course everything that came from the top here. So this is essentially Kirchhoff's current law, which says that in a node in a circuit, all the current that goes in must be equal to the current that goes out. So let's summarize. When we put resistors in parallel, then we essentially add additional current paths, and that results in a reduction of the total resistance. So it's easy to calculate the current that goes through all these resistors. Essentially what we do is we simply use Ohm's law, and we calculate the current in each of the resistors. And so we get here the total current is just the voltage across the resistors divided by resistor 1 plus the voltage divided by resistor 2. And so if we pull the voltage out, then what we're left is just 1 divided by resistor 1 plus 1 divided by resistor 2. So we can generalize this and say that 1 over the equivalent resistor with which we could replace all these resistors in parallel is just the reciprocal values of all the resistors that we have in the parallel setup. So if we look at this example, with here two 1 kilo ohm resistors, so we have 1 divided by 1000 ohm plus 1 divided by 1000 ohm. That is just 2 divided by 1000 ohm, so we can calculate the equivalent resistor as being 500 ohms. What we also saw in the simulation is that if we look at the current that goes into a node of the circuit, this current that goes in needs to be equal to the current that leaves the node. And so in this case, this means that the current that goes in, it splits up into these two currents that go out, but when we add these two, they need to be exactly the same like what goes in. That makes sense because there is no way for electrons to go anywhere else that we put into the node than having them leave here in those two current branches. So we can say that adding up the currents that go in and out of the node, that just needs to be 0. Right, and of course here the currents that go out, they have a negative sign relative to the current that comes in, because this goes into the node and this here is leaving the node. So we can generalize this if we have n connections in a point of the circuit, that we simply add up all the currents that go in or out of that node, and that needs to be 0. So this is known as Kirchhoff's current law. The last part of this tutorial is about power. Power is energy per time, and so when we talk about power in components of a circuit, then what we think of is the amount of energy that is consumed by a load per time, or being provided by a power source per time. So what this means is, if a load consumes energy at a certain power level, then this energy needs to be dissipated to the environment, usually as heat. But if you think of an LED or a speaker as load, then part of that energy is of course dissipated as light or as sound, for these two examples. In any case, when energy is dissipated, it means that that load needs to be able to dissipate the power. It needs to be properly dimensioned, that it is able to take the heat, if you will. One can show that in an electronic circuit, power is just the current multiplied with the voltage. So we have P equals I times V. So in this graph here, we see the current voltage curves of two resistors, like we saw it earlier. So here we have the 1 ohm resistor, and here we have the 10 ohm resistor. And remember, in the 1 ohm resistor, if we apply the same voltage like at the 10 ohm resistor, the 1 ohm resistor gives us a 10 times higher current than the 10 ohm resistor. So that's just simply Ohm's law. Now power is I times V, so we can just think of it as these rectangles that that are defined by the voltage and the appropriate power. And so you see here that in the 1 ohm resistor we get a big rectangle, and in the 10 ohm resistor we get a small one. That means that the power dissipated at the same voltage in the 1 ohm resistor is 10 times higher than the power that is dissipated in the 10 ohms resistor. I did an experiment for you to illustrate the concept of properly dimensioning an electronic component for the power that we expect it to dissipate. So what we have here is a quarter watt, 0.25 watt resistor with 220 ohms. Let's see what happens as I ramp up the voltage. So this is a lab power supply. So on this display you see the voltage, and over here you see the current. So let's see what happens. So I'm going slowly up, and now I'm more than 7. And so if you calculate now 8.5 times 0.04 amps. So here now we have a power of 0.34 watts in the resistor. So we have exceeded the rating of this resistor, that's only a quarter watt. So if you would touch it now, it would start to get pretty warm. And let's see what happens as I go on with turning the voltage higher. So now we're about 2 watts going through it, and we see that there is a little bit of smoke developing. Now the paint is cooking, and it's almost catching fire now. So it's glowing very bright, and I go a little bit higher. I turned off the light so we can see it glow better. And now basically at 38 volts it gave up, and what that means is, so the current is 0 now. That means that the conductive path in there completely evaporated. So the lesson that we learned here is that a 220 ohm resistor that's rated for a quarter watt power dissipation should not be ran with a higher voltage than about 7 volts. If you wanted to pass a higher current through it, so that would mean use a higher voltage on it, then you would have to get a resistor that is rated for a higher power dissipation, so it would look a little bit bigger than this one. The experiment showed us that it is a good idea to calculate the to be expected power dissipation in components that we have in an electronic circuit. And there are two convenient formulas that directly relate the current and the resistance and the power, or the voltage, the resistance and power. So power is the current squared times the resistance, or it is the voltage squared divided by the resistance. Of these two formula, probably the one with the voltage is the more important one, because one typically knows the voltage that is applied to a load in an electronic circuit. I made a graph over here for the two resistors, for the 1 ohm and the 10 ohm resistor, where the power is plotted versus the applied voltage, so we get these two parabolas. And we see here that the 10 ohm resistor could be a much lower power, could have a much lower power rating than the 1 ohm resistor. Right, so the 10 ohm resistor, we could have a 0.05 watt resistor, so a really small one, while for the 1 ohm resistor we would have to have a 0.5 watt resistor. In practical terms, this means the 10 ohm resistor could be a really small one, while the 1 ohm resistor would need to be a much bigger one to survive the heat dissipation. This concludes our Electronics 101 tutorial about resistors, voltage dividers and power. Thanks for watching.